Okay, so you know how sometimes you look at a topic and you just think to yourself, there's no way I have time to learn all this.
Yeah.
And honestly, sometimes you're probably right,
Or
but
you don't always have to learn everything you know,
exactly.
just the important stuff.
Right. And that's where we come in.
That's right.
This is the deep dive where we help you understand complicated things
Right.
without like having to go and get a PhD or something.
Yeah, exactly.
So today we are going to take a look at how electricity gets from a power plant
Like all the way to your house.
all the way to your house.
Yeah. So,
To your lights and your devices.
all right, we've got these source materials here that are kind of like blueprints, you know?
Yeah, they are pretty detailed.
And what we're going to do is we're going to follow the path of electricity,
Yeah, like where does it start?
starting at the source,
At the source, right?
the generation, and then we're going to look at why they increase the voltage so much,
Oh, yeah, that's a good point.
the transmission.
Why does it have to be so high?
And then we'll follow those transmission lines. We'll see how it gets stepped down, and then ultimately all the way into your house, to your outlets and all that.
That's awesome.
And we've also got some questions here that we'll go over at the end just to kind of solidify everything.
Love it.
Yeah.
Okay, so let's start right at the beginning with section 4.2, which is called Source of Electrical Generation.
Okay.
And this is also illustrated by figure 4.1.
All right. So this section basically tells us where the electricity comes from.
Right. The different ways we can generate it.
Yeah, like the main ways, right? So it talks about fossil fuels,
Right.
coal, natural gas, petroleum,
The big ones, yeah.
nuclear energy.
Mm-hmm.
It also covers renewable sources like gas turbines, and then like hydro turbines,
Daughter, yeah.
wind turbines, and then solar photovoltaics,
Right.
which basically convert sunlight right into electricity.
Yeah. So there's a bunch of different ways we can generate this electricity.
Yeah, a bunch of different ways.
All right. And then figure 4.1. I really like this figure because it gives us a really clear visual representation of these different methods.
Yeah, it's great.
You know, we see like the fossil fuels.
The smokestacks, right?
Yeah, it looks like a plant with smokestacks.
Yeah.
You know, then we see like the nuclear symbol.
Right.
We see the solar panels.
Yeah.
We see the wind turbines.
Yeah, it's really good to visualize everything that's going on.
Right. And it really emphasizes, how many different ways there are to generate electricity.
Yeah, absolutely. And section 4.2 goes on to say something really important that's kind of reinforced by the answer to the first question in our other document.
Okay.
It says that most of our electricity is still being generated using steam turbines.
Really?
Yeah,
So,
I would have thought.
yeah, a lot of people
Definitely
think,
more like solar and wind these days.
yeah, it seems like there's so much focus on that.
What
But actually,
is-
the bulk of our power still comes from either burning fossil fuels or harnessing heat from nuclear reactions to create that steam. Okay, interesting. So we've got the electricity now,
Right, we've got the power.
but it can't just travel in that raw form, can it?
No, it can't.
We have to do something to it.
We've got to step it up.
Okay, so let's move on to section 4.3. Step up transmission voltage.
Okay.
And this is illustrated by figure 4.2.
Yeah, so this is all about efficiency
Okay.
over long distances.
So when you think about how far electricity has to travel sometimes,
Yeah, it's got to go, hundreds of miles,
hundreds of miles,
sometimes even further.
right, it loses energy along the way, I guess.
It does. Yeah, some of it gets lost as heat as it travels through the wires.
Oh, okay.
And so the best way to reduce that loss is to actually increase the voltage.
Yeah.
It's kind of counterintuitive,
Yeah, it seems like if you make it stronger, it's going to lose more energy, but
It's like if you want to send a lot of water through a really long, narrow pipe,
okay.
you want to pump it with a lot of pressure. It's the same idea with electricity.
Oh, okay. That makes sense.
Yeah.
More pressure, less loss over those long distances.
Exactly.
Cool. Okay, so that's why they step up the voltage at the power plant itself.
Right at the source.
Yeah.
And figure 4.2 shows this really well. You can actually see the generating plant and then these big transformer units.
Yeah.
And it shows, like, for example, they'll take an initial voltage of 13.8 kilovolts.
Right.
And then they'll step it way up
Way up.
to a transmission voltage between 69 kilovolts and 765 kilovolts.
Wow. That's a huge jump.
Yeah, huge jump.
Okay, so they're putting a lot of pressure on this electricity.
Yeah, a lot of pressure.
Okay. And question 2 points out that the transformers at the facility are specifically there to do that step up.
Yeah, to make that transmission more efficient.
Okay, great. So now we've got this high voltage electricity.
Right, it's ready to travel.
It's on the highway,
It's on its way.
ready to go long distance.
Yeah, exactly.
So how does it actually travel? Well, let's take a look at section 4.4, which is high voltage transmission lines.
Okay.
And figure 4.3 shows us what that looks like.
Okay.
So basically, section 4.4 says that the most cost-effective way to move this electricity from the power plant across long distances is to use these high-voltage transmission lines.
Right.
And to keep it at that high voltage until it gets to these step-down substation transformers.
Okay. And we see those all the time, right?
Yeah, you see them.
The big metal towers
Yeah.
with a thick cable.
Those huge pylons.
Yeah, the pylons really
Right,
tall,
and sometimes they're really tall.
especially if you're going over a road or something.
Yeah, they're huge.
It makes you realize how much power is going through those things.
Yeah, for sure. And the author's comment in that section actually points out something really important.
Okay.
It says that by increasing that transmission voltage, they're actually reducing the voltage drop and the power loss as that electricity travels.
Right. So it's not just about efficiency. It's also about reducing how much electricity is lost.
Right. Both of those things are really important.
Okay. That's really interesting. And question 3 tells us that that's why high voltage is used for this economical transfer.
Exactly.
Okay, great.
Yeah.
So we've got our electricity traveling efficiently across long distances,
Yeah.
but obviously it can't stay at that super high voltage forever,
No, it can't.
especially when it gets to our homes and businesses.
Yeah, that would be dangerous.
Yeah. So
It needs to be reduced.
It needs to be brought down to a
Right.
safe level.
okay, so that's where we get to section 4.5, primary distribution voltage,
Okay.
and figure 4.4.
All right, so once those high voltage lines reach a step-down substation,
Right.
they have to reduce the voltage to something called primary distribution voltage.
Okay.
And this is usually between 13 kilovolts and 34.5 kilovolts.
Still pretty high.
Still pretty high, yeah, but way lower
Right, way lower.
than that transmission voltage.
Yeah, it's coming down a bit.
Yeah, and question 4 actually confirms that this voltage is stepped down at the substation.
Perfect.
Yeah.
And then figure 4.4 shows us a visual representation of this process.
Yeah,
We see the high voltage lines going into the substation,
right.
which looks kind of like a fenced off area with a bunch of equipment.
Yeah, a lot of equipment in there.
Right. And then coming out of the substation are lines carrying this lower primary distribution voltage.
Exactly.
So it's kind of like the electricity is going from the superhighway to like major roads now.
Yeah, that's a good analogy.
Okay, so now that we've stepped down the voltage a bit, we need to get it distributed further.
Yeah, exactly.
Right, so that brings us to section 4.6.
Yeah.
Primary distribution wires.
Okay.
And figure 4.5.
All right, so these primary distribution wires are basically the next stage of the journey.
Yeah.
They run from that step-down substation to what are called distribution transformers.
Okay.
And these are the transformers that we probably see the most often.
The ones at the poles.
Yeah, the cylindrical ones on the poles.
Right.
Or sometimes they're on the ground in those green boxes.
Yeah.
Pad-mounted transformers.
Okay.
So the text tells us that those primary distribution wires are delivering power to either the pad-mounted ones, which are usually underground,
Mm-hmm.
or to the pole-mounted ones for overhead service.
Right, and questions 6 and 7 actually tell us that.
Exactly.
Perfect.
Yeah, so, if you look at figure 4.5,
Yeah.
it gives us a visual of both of these.
Right.
Part A shows us the overhead wires running along the poles
Right.
and connecting to a transformer on the pole.
Yeah.
And then part B shows us the underground wires
Right.
going to that pad-mounted transformer.
Really nice illustration.
Yeah, so now we're getting even closer to the buildings.
Yeah. So we've come down from the highway to the major roads,
Oh.
and now we're getting to like the side streets.
Exactly.
Okay, so at this point, we're still not quite at a voltage we can use in our homes and businesses.
Not yet.
Right.
It's still too high.
Yeah, it needs to be reduced even further.
It does.
Yeah.
So that's where we get to section 4.7, secondary distribution voltage,
All right.
and figure 4.7.
Okay.
So this is where those distribution transformers really come into play. They
Mhm.
take that primary voltage.
Remember, it's still between 13 and 34.5 kilovolts.
Yeah, still pretty high.
Yeah.
And they reduce it even further
Got it.
to what's called secondary distribution voltage.
Okay, and that's the voltage we actually use in our homes.
Right. This is the range that we see in our outlets.
Or the 122.40,
Yeah, 122.40.
or if you have a business, maybe 122.8.
Yeah, or 277.480.
Okay.
So this is the voltage that actually powers everything.
Yeah, so we've come all the way down from those super high transmission voltages
done?
to something we can actually use.
Exactly.
Okay, so question 8 confirms that the transformers reduce that primary distribution voltage.
Yeah, that's the main job.
to the usable secondary distribution voltage.
Exactly.
Okay, and then figure 4.7 shows us a diagram of this process.
Yeah.
We see the higher primary voltage on one side of the transformer,
Right.
and then the lower secondary voltage coming out the other side.
That's it.
Perfect.
Yeah.
Okay, so now we're almost there.
We're almost at the finish line.
We've got the right voltage.
Yeah.
How does it actually get to our property?
Okay, so this is where we get to section 4.8, service drop and service lateral.
Okay.
It figures 4.8 and 4.9.
Right, so this is the final connection.
Yeah, the last mile.
Right.
So section 4.8 tells us that there are two ways for that power to get to us,
Okay.
either through overhead wiring, which is called a service drop,
Mm-hmm.
or underground wiring, which is called a service lateral.
Okay, and question 9 confirms those two options.
Exactly.
Great. And then figure 4.8 shows us what a service drop looks like.
Yeah, you see those wires running from the utility pole, often where that distribution transformer is located.
Yeah.
And it goes right to the roof line of the building.
Right.
And the text specifically calls those wires the utility service drop.
Okay, and question 10 also tells us that.
Yeah, question 10 confirms that.
Okay, cool.
Yeah.
And then figure 4.9 shows us the service lateral.
Yeah, so here the wires are underground,
Right.
running from the transformer to the building.
And question 11 tells us that those are called the utility service lateral.
Exactly.
Perfect.
Yeah.
Okay, so whether it comes overhead or underground,
Right.
that secondary distribution voltage delivered through the service drop or lateral,
Yeah.
that's what powers everything in our homes.
Exactly. That's what we use every day.
We finally made it.
We followed the whole
A
path.
whole journey of electricity.
Yeah, from the power plant all the way to your house.
Awesome.
Yeah.
Okay, so let's quickly go back to the questions from 4.2 PDF,
Okay.
just to make sure we understand everything.
Good.
Okay, question 1 says, most electricity is generated with steam turbines using. And the answer is fossil fuels and nuclear power.
Right. And we talked about that earlier.
Yeah, section 4.2
Yeah,
and figure 4.1.
exactly.
Okay, question 2. Transformers at the utility generating facility blank voltage for transmission distribution to between 69 kV and 765 kV.
Okay.
The answer is step up.
Right, because they're increasing the voltage.
Yeah, we saw that in section 4.3 and figure 4.2.
Yeah, that was a big jump.
Huge jump.
Okay, question 3.
Okay.
The most economical way to move electrical energy from the generating facility over long distances is to transmit the electrical energy at blank voltages to distribution step-down substations.
The answer is high.
Right? High voltages are the most efficient for those long distances.
Yeah, section 4.4 in the author's comment
Yeah.
talked about that. Okay, question 4. Once high voltage transmission distribution power reaches the step-down substation, the voltage is blank. From transmission voltage to primary distribution voltage, which is between 13 kV and 34.5 kV.
Okay, and the answer there is step down.
Right, they have to reduce that voltage at the substation.
Yeah, section 4.5 and figure 4.4 show that.
Okay, question 6. Utility primary distribution wires provide power to distribution transformers mounted on poles next to the building or structure served.
Okay, and the answer is overhead.
Right, because those wires are running along the poles.
Yeah, we saw that in figure 4.5a.
And section 4.6.
Yeah.
Okay, question 7. Utility primary distribution wires provide power to pad-mounted distribution transformers located near the building or structure served.
All right, so the answer there is underground.
Right, because those wires are buried.
Yeah, figure 4.5b shows that.
And section 4.6?
Exit.
Okay, question 8. Utility distribution transformers blank the primary distribution voltage to secondary distribution voltage for customer use.
Okay, and the answer is reduce.
Right, because they have to step down the voltage again.
Yep, section 4.7 and figure 4.7.
Okay, question 9. Power from utility distribution transformers is delivered to the customer by utility blank wiring.
Okay, the answer is overhead or underground.
Right, because it can be either one.
Yep, section 4.8 talks about that.
Okay, question 10. Overhead wires from the utility primary distribution transformer to the premises are called the utility blank.
And the answer is service drop.
Right, we saw that in figure 4.8a.
Yeah, and section 4.8.
Okay, last one, question 11. Underground wires from the utility primary distribution transformer to the premises are called the utility blank.
The answer is service lateral.
Right, figure 4.9b.
Yep, and section 4.8.
Perfect. Okay, so we got all the questions right.
We did it.
Awesome.
We successfully followed the path electricity.
Yes, we did.
Yeah.
All right, so we also have a couple extra questions here that touch on some other interesting concepts.
Okay.
So question 15 says, a common application of thermoelectricity is a blank, which is a sensor that measures temperature.
And the answer is thermocouple.
Right. So this is kind of a cool example of how we can actually convert heat energy into electrical energy.
Yeah, for a specific purpose.
Right. In this case, to measure temperature.
Exactly.
Really interesting.
Yeah.
Okay. And then question 16. Piezoelectricity is the conversion of blank or vibration into electrical energy necessary to move electrons within a circuit.
Right. And the answer is pressure.
So this shows us another way to generate electricity,
Right.
not through burning fuel or nuclear reactions.
But through actually like physically deforming certain materials.
Wow. Okay. So we've covered a lot of ground today.
We have.
We started at the power plant
Yeah.
and we followed the electricity all the way to our homes.
All the way to the outlets.
Yeah. We saw how it gets stepped up in voltage
Right. For efficient transmission.
and then stepped down.
Multiple times
Yeah.
to get to a safe, usable level.
Exactly. So quickly recap, it usually starts at a power plant,
Right.
often powered by fossil fuels or nuclear energy.
Yeah.
That initial voltage gets increased,
Way up for
Yeah.
long distance travel.
right, using those high voltage transmission lines.
Yeah, those big towers.
Exactly.
All the time.
And then when it reaches a substation,
Yeah.
the voltage is reduced to primary distribution voltage.
Right.
And then that's carried by primary distribution wires to local transformers,
Right.
which then lower the voltage even further to secondary distribution levels.
To what we use.
Right. And then finally reaches our home or business through a service drop or a service lateral.
Exactly.
Phew.
Yeah.
That was a lot.
It was a long journey.
It was. But I think we got a really good understanding of how this complex system works.
I think so too.
Yeah, it's amazing how much goes into just getting electricity to our homes.
Yeah, it's pretty incredible. When you think about all the steps involved.
So I'm curious, what do you think the future of electricity delivery looks like?
Oh, that's a great question.
You know, we talked about all these different stages and components, but technology is always changing.
That's true.
So what kind of innovations do you think might shake things up in the coming years? Something to think about.
Yeah, definitely something to think about.
Okay, well, thanks for joining us for this deep dive,
Yeah, thanks for having me.
and we'll see you next time.
See you later.